Algebra 2, starting chapter 10, section 1, it's called Sequences as Functions. I'm sure some of you remember sequences from Algebra 1. We want to kind of revisit this a little bit and then see where we can build on it from here. So let's start by going over some definitions here. First off, sequence, we're going to have a set of numbers that are in a particular order or a pattern. Set of numbers in a particular order or pattern. Know your definitions. These could be things that pop up on a Google quiz or something in your future. Term, that's going to be each number in the sequence. So you've got a bunch of numbers in a series here, some pattern in between them. Each individual number will be called a term. There are finite sequences which have a limited number of terms. And we'll show you notation and how you can decide one way or the other. They're infinite, and this will have unlimited number of terms. And again, there'll be a way to tell with what we're dealing with. Now, when we talk about the terms, notation-wise, we'll see this. So we'll see A subscript 1, that's going to represent the first term. A with a subscript 2, second term, and so on. You'll see all the way down to A subscript n. That'll be the value of your nth term, whatever that happens to be. So now, a couple different things here dealing with our sequences that we need to have straight. And that would be, first off, a sequence as words. So we see it written out as we're dealing with stuff. The domain, so we're going to be dealing with domain and range. The domain will be made of natural numbers. That's a key ingredient. So make sure you know the definition of natural numbers, or review your definition of natural numbers. There's only a certain amount that you can choose from. So please be careful with that, because you'll be tested on whether you have a sequence or not based on that stuff. Range. Range is going to be made of real numbers. So range could be anything. Domain, x values, can only be natural numbers. Keep that in mind, because sometimes you might have to graph as well. So domain and a range. Okay, so now as we look at this in terms of just numbers, your domain, natural numbers can only start at 1. No decimals, no fractions. 1, 2, 3, off to whatever. Your range then, these will be different values of whatever's going on. So it's a function, so something's going on with it. So a sub 1 matches up, a sub 2, a sub 3, a sub n, they match up, they correspond as that certain number in the list. So just a little bit of an example here. So here we have a finite solution. So we got our fancy brackets back out. With a finite solution, I'll just give you 3, 6, 9, 12. Okay, what's our domain? It's not listed. This is the key ingredient. You got to know what natural numbers are. I see 1, 2, 3, 4 terms. So your domain, 1, 2, 3, 4. There's my first term, second term, third term, fourth term. That's what a domain is. The range is then the value, 3, 6, 9, 12. So that'll be a sub 1, a sub 2, a sub 3, a sub 4, in this case with only 4 things. Now notice the difference. If it were an infinite solution, you're going to see the 3 dots, dot, dot, dot. So it starts at 3, 6, 9, 12, and then carries on. It goes on off to, get ready for it, infinity. So what's your domain going to be? Now, well, we still got a first term, so it's going to be all natural numbers. 1, 2, 3, 4, and then off to infinity, whatever that number happens to be. So we look then at what the range is. Notice the difference. Set builder notation comes back into play. I ran out of room So that's why it's on the second line here. You arrange y such that y is a multiple of 3. We can all see that's what's going on. That's our pattern. And then y has to start off greater than or equal to whatever your first term is. So notice the difference here in notation, whether I have a finite solution, or, finite sequence, or an infinite sequence. ... Notice all the differences that come into play. All right, page 2. So what is an arithmetic sequence? There are different types along with just being finite and infinite. We have what are called arithmetic and geometric. Arithmetic bases on the pattern that you find. So in an arithmetic sequence, each term is determined by adding a constant value. Now, this is a misnomer for some of us. Adding a constant value, we think adding is always plus, it's always plus, it's always plus. It could be adding a negative, or in other words, subtraction. Keep that in mind. Adding means you could also be adding a negative. So be very careful with that. So what are we doing with this constant value? Adding to the previous term. You could be adding a negative. Remember that. And this constant is called the common difference. And it's represented by D. D, difference, I know. Pretty astounding in terms of what we have here. So, let's look at just a real quick example with this. Let's say I had 12, 9, 6, 3. Many of you will look at this and say, oh yeah, I'm subtracting 3. I get it, that's fine. Technically speaking, we are adding a negative 3. Adding a negative 3. Adding a negative 3. So I'm following adding a negative. This, we're going to write it out as we're subtracting 3 each time. Just something to keep in mind, a little play there on the words in terms of knowing my exact definitions, what we're dealing with. Okay. So, let's see how I want to do this. I got all sorts of stuff on here. Here we go. All right, so looking at this example, we see we have a series, a sequence, if you will, of 5, negative 6, negative 17, negative 28. The question is this arithmetic or not? Well, let's see. Is there a common thread, a common theme, a common difference? So to go from 5 to negative 6, we subtract 11. To go from negative 6 to negative 17, we subtract 11. To go from negative 17 to negative 28, we subtract 11. So there is a common difference from these 4. That's our pattern of subtracting 11. So yes, this is. Yes, we have an arithmetic sequence. Okay. So let's look at this example. Is this arithmetic? Same thing. Look and see if you've got a pattern as we do this. Well, from a negative 4 to 12 is adding 16. From 12 to 28 is adding 16. And from 28 to 42 is adding 14. So no, this is not arithmetic. Plain and simple. How do you tell if it is or isn't? All right. Now, there's a formula that goes with this. Now, the book goes through a lengthy process of using point, slope, and linear equations to do this. Let's cut to the chase. There is a formula for arithmetic sequences, and the formula looks like this. A sub n equals a sub 1 plus d times the quantity of n minus 1. I know you've seen this from Algebra 1, so let's work through it again. So as I work on this problem, let's see. A sub n, well, that, ladies and gentlemen, will stand for the nth term, the value of it. The value of the nth term, the range, if you will. So that's the value of the nth term. A sub 1 will be whatever your first term is. The value of it, again, remember, those fell into the range category using the letter A. D will be your common difference. N will now be any natural number. Any natural number. Look at it this way. It's the place we're looking for. Place we're looking for. So let's apply this to an example and see what we can come up with. So our example looks like this. There we go. At halftime, the VH band formed a pyramid as part of the show. In row 1, there was 1 member. Row 2 had 3 members. Row 3 had 5 members. So you can see a pyramid is being formed as they play their halftime songs. And this pattern continues. How many members would be in row 14? Well, you got a couple options here. You can start 1 member, and then you go 1, 2, 3 members, 1, 2, 3, 4, 5 members. Row 1 had 1, row 2 had 3, row 3 had 5. You can keep doing that for a while, or we can apply our formula. Our formula reads a sub n, a sub 1 plus d, oops, no equal sign there, sorry, n minus 1. So let's work. Let's work through this. Excuse me. So what do we have? What values do we have? Do we have the first term? We do. So row 1, that would be a domain, has 1 member. So we've got a 1. A sub 1 equals 1. Do we have a common difference in what's going on here? Well, row 2 had 3 members. Row 3 had 5 members. So I had 2. I had 2. So we keep adding 2 to it. So D is equal to 2. We want the 14th row. Notice domain, domain. So that's going to be domain. In other words, what we're looking for, the place we're looking for, row 14. The value will be here. How many members are in there? Well, let's do the work. 2 times 13 plus 1 So because we have a geometric sequence on it, same increase of 2 each time, you're going to have 27 members. In row 14. Found a pattern that existed. Now we can find anywhere through that. And again, knowing what we have, we can manipulate and find all sorts of different things with this. Okay, last part of this section then is we have a geometric sequence. Okay, arithmetic, common difference. You're adding or subtracting something from each term constantly. So geometric, each term is determined by multiplying. Again, a misnomer. We're focused on all multiplication. You'll see this a lot. So where's the division come in? Multiplying by a fraction. Sometimes a fraction. Not always, but at times. Multiplying by a fraction. That's how you get your division taken care of. Also, it's got to be non-zero. I mean, we should all know that we're multiplying by 0, but it's a stipulation, so non-zero. So each term is determined by multiplying the previous term by a constant. This constant would be our non-zero. It can be a fraction at times. So this is called a common ratio. So now we're looking, our pattern is multiplication by some non-zero. Let me focus that a little bit. I guess so. So multiplying by some non-zero thing to get the next term. So let's look. Question is, do we have a geometric sequence or not? Geometric sequence or not? Now, many of you are going to see, okay, I multiplied by -3, I got that, multiplied -3, multiplied by -3. There's nothing wrong with that. I am offering you this for when we get the ones that we can't just see times 2 and so on. Take the next term and divide by the previous. 6 divided by -2. -18 divided by 6. 54 divided by -18. Why am I showing you this? When this doesn't come to you very quickly, check it this way. Am I getting the same answer as I divide those through? So the answer is yes. Our common ratio is -3. So check it out that way. Looking here, again, you can do some things in your head. I get it. You know, we're times 2. Times 1.5. Well, right off the bat, I know it's not going to be. And then this would be times 1.3 repeating for you decimal fans, or 1 1/3. Again, 16 divided by 8, 2. 24 divided by 16, 1.5. 32 divided by 24, 1 point repeating 3. Not the same pattern. So no, this is not a geometric sequence. Yeah, there is a formula for a geometric sequence as well, and it goes as follows. Notice there are some similarities, but also a difference or two. So we'll have a sub n equals a sub 1 times r to the n minus 1 power. So let's look through this. A sub n, as before, is going to be your nth term, the value of it. That would be the value of our nth term. Y value, if you will. A sub 1 will be your first term. R, that's your common ratio. And then n will be any natural number, which is, again, the place that we're looking for. Let's do one quick example here. We'll get more in depth with our examples as we move on to the next section or two. But just real quick, if I gave you 32, 8, and 2, and then ... All right, find the next three terms. So step 1, find the common ratio. Now let's see, divided by 4. Some of you say dividing by 4. I get it. But when you're taking tests, ACT, SAT things, they're not going to say the division, they're going to do the multiplication by definition. So we're multiplying everything by 1/4. So we'll take 2 times 1/4 and get 1/2. We'll take 1/2 times 1/4, and this is where it works out a little bit nicer for us. We'll get 1/8. And then we'll take 1/4 times 1/8 and get 1/32. 1/32. So as we move forward this week, and I'll have this posted as well, your assignments are going to be as follows off of this. I'm going to give you page 663, numbers 1 through 23 odd. And we're going to NORI, which I gave you as bonus at one time to get you used to it. We're going to do lesson 12-1. They'll both be due on, I'd like them both by Friday, this for sure. It would be nice if you have this done by Friday, but I will give you the weekend to get used to it. So you'll see that, but again, I'd like Friday just so I can work on getting the grades and getting those in for you. Don't remember how to do NORI? Pop into our help sessions on Monday and Wednesday, and I can walk you through that.